Alright, I'd like to finish what we started talking about in class to give you some notes and really solidify our understanding on this concept. So we started talking about something called a cross-similarity matrix. And this was used to describe what I call time-ordered point clouds. So time-ordered point clouds. These are just samples of a curve in some dimension, ordered by time. Okay. So the curve traces out some path over time, and I'm going to sample the points. Now the way I arrange the points is actually in a matrix. So each point is in some space with some number of dimensions. Every dimension is a different column of this matrix, and every sample is a different row. So as an example, I have, let's say I have this figure 8 curve, also known as a special case of a Lissajous curve. So this is a curve which is parameterized as follows. I write it as, so my x-coordinate is equal to, well, let me check down here to make sure I get this right. Yeah, so the x-coordinate is equal to cosine of t, or I guess we can say cosine of 2 pi t, and the y-coordinate is equal to sine of 4 pi t, actually. So the y-coordinate ends up going through 2 cycles for every 1 cycle of the x-coordinate. Turns out that makes a figure 8. Alright, so what I'm doing here is I'm creating 2 different samples of the figure 8. And they're going to be sampled differently. So I'm going to take different points along these figure 8 curves. The first one I take uniform samples. The second one I start slow at the beginning and then speed up. But notice how, okay, so I have my x-coordinate, which is cosine of 2 pi t, and I have my y-coordinate. So my x-coordinate I'm putting along the first column. So that's what this means. Slice down all the rows, first column. My y-coordinate I'm putting along the second column. Okay, so that's how we're representing these time-ordered point clouds. So if I can go to plot these, what I'll see is, so here's the x-coordinate, here's the y-coordinate of the first one. Let's see how to do it here. I had, okay, it's reds for the first one. And now I'll go and plot the second one as well. And I'll use blues on this one. Okay, so let's just look at what this looks like. And we see an error. Oh, I meant to say. Okay, I'm just trying to color the points according to their time. Okay, there we go. Okay, so here are the 2 different curves that I get. Bright means beginning of time, darker means the end of time. Okay. So we see these are both figure 8s. The left one starts off faster. You see there's bigger space between the samples than the other one. This one, we have a lot more samples in the beginning. But this one speeds up, and it speeds up more and more and more. Okay. So what we can do is compute a cross-similarity matrix between these 2. So a cross-similarity matrix C is a matrix, so let's see, a cross-similarity matrix C on a time-ordered point cloud, or between a time-ordered point cloud X with M points and a time-ordered point cloud Y with N points is a M by N matrix C, or I guess I'll call it D, so that Dij is equal to the distance between X I and y j. Okay, this is what this means. So there's a formula for this, which is a generalization of the Pythagorean theorem. So we say in particular, dij is equal to the sum over all dimensions. So if there are d dimensions, that would be of x ik minus y jk. So it would be this quantity squared, and then the square root of the whole thing. Okay. So let's look at this and see if we can code it up. Okay, so this is my formula for the distance between the ith point in my first point cloud and the jth point in my second point cloud. All right. So I have code that does this very quickly, but let's just write out kind of just from the definition how we would do this. So I'll say way one, brute, sort of brute force Pythonic. So way one, Pythonic CSM computation. So I would say def get CSM. Oops, let me make sure I'm writing this in code. Get CSM Pythonic xy. All right, so I say m is the number of points in x. Oops, I just noticed this was messed up. Okay, m is the number of points in x, so m is equal to the number of rows in this x matrix, x.shape 0. N is equal to the number of columns in y. Sorry, the number of rows in y. Let me just allocate some space for my array. So it's going to be an m times n matrix, or I guess I called it d, didn't I? Okay, so let me loop through all the rows of this matrix, and let me loop through all the columns in this matrix. So for each row, I'm going to loop through every column. And now I'm going to say d at row I, column j, is equal to the square root of the sum of xi. Well, this is kind of a mix of Python and NumPy. But sum of xi minus, so the row I of x minus the row j of y, quantity squared. So I want to take the difference of every element, and I want to square that. Oops, hang on, the square needs to be, so it should be the quantity xi minus yj squared. And then we sum, so okay, so we square all the differences, then we sum them all up, and then finally we take the square root. Okay, so we took the differences, we squared them, we summed them, and then, yeah, we took the square root. Oh, it's because I have an extra parenthesis there. Okay, there we go. All right, so that is one way to compute the cross-similarity matrix, and that will work just fine. But there's another way to do it that's very, very fast. And I've written this up here. I'm happy to explain it to people who want to know more, but we're just going to take it for granted for now. Okay. All right, so let's use this, and let's look at the cross-similarity matrix for these two figure eights, between these two figure eights. I meant to say get CSM fast. Okay. And what do we have problem with here? Whew. Big errors. It's telling me I'm using the wrong color map. Oh, I meant to say, okay. This goes up here. Okay, and I'm not, okay, this was left over from class. I'm not going to use this anymore. Okay. Almost there. Okay. And I don't need this. Oh. What did I call this? I called this C, not CSM. Okay. Alright, and let me make this big enough to look at here. Okay, so what we see, so here are the two curves. I've lined them up next to each other. And I actually blew up the second one a little bit just so you could see them. So anyway, along the rows I have indices corresponding to points on the first curve. Along the column I have indices corresponding to points on the second curve. And what I see is that, the distances between the two curves are small, kind of along this whole path in this cross-similarity matrix that starts in the upper left and ends up in the lower right. Okay, so let's pause on that for a second, and then I'll start to explain a little more about this path.